Okay, so if you've ever had a dental filling, you've got a little piece of modern polymer chemistry right there in your mouth. But what you don't feel is the incredible stress that builds up inside that filling as it hardens. It's actually a huge reason why they fail. But now, some really brilliant chemistry is offering a solution. What if we could design materials that literally know how to relax? So here's our game plan for this explainer. First, we'll dig into why stress in fillings is such a big problem. Then, we'll look at this amazing idea of a polymer network that can adapt on the fly and the chemical switch that makes it all possible. We're definitely going to look at the data, see how this tech actually performs in the real world, and then wrap up by talking about why this is such a huge shift for material science.
All right, let's get right to the heart of the matter.
You know that little blue light your dentist uses to cure a filling? Well, the moment they turn that on, they're starting a race against a fundamental problem in physics. Now look, fillings can fail for a bunch of reasons, but one of the absolute biggest culprits is something that happens at the molecular level the second that material starts to harden. And here it is. This is our main villain, polymerization shrinkage stress. Think about it. You start with this liquid resin full of tiny individual molecules, the monomers. When they get hit with that light, they start linking up, forming this strong, tangled, solid network. But as they do that, the whole structure pulls together and shrinks. And since it's bonded to your tooth, which doesn't shrink, it can't go anywhere. So instead, it just pulls and pulls, creating this massive internal stress that can literally rip the filling away from the tooth, leaving tiny gaps for bacteria to get in.
For the longest time, the goal in dentistry was just to make materials that shrink less. But that's incredibly hard. So what if you could change the game? Instead of fighting the shrinkage, what if you could design a material that's smart enough to manage the stress it creates? And that's where this idea of an adaptable network comes in. So on the left, you've got the old way of doing things. Once those chemical bonds form and lock in, that's it. They're stuck. All that stress from shrinking just gets baked right into the material, permanently. But on the right, we have a covalent adaptable network, or a CAN. The huge difference here is that the network itself is dynamic. It has a built-in way to break and reform its own connections, which lets the whole structure kind of shuffle around and release that stress as it's forming. It's a total game changer. And the engine that makes all this dynamic shuffling possible is this really elegant chemical process. It's called addition fragmentation chain transfer, or AFCT for short. This, right here, is the secret sauce.
So, how does this molecular magic trick actually work? Well, it all boils down to a very special chemical group that acts like a tiny, reversible switch inside the polymer network.
Okay, here's the play-by-play. Researchers put a special molecule containing an allyl sulfide group right into their resin mixture. Now, during polymerization, you have these highly reactive things called radicals flying around. One of these radicals can come in and attack the allyl sulfide group. When it does, it temporarily breaks a bond in the main polymer chain. That's the fragmentation step. But here's the cool part. Instead of just breaking things, the bond almost instantly reforms, but often in a new, less strained spot. This little swap allows the whole network to subtly rearrange itself and just let go of that built-up tension.
Now, the really crucial thing to get here is that this isn't a one-time thing. The whole process is catalytic. That radical that kicked everything off, it gets regenerated at the end of the reaction, so it can pop off and find another strained bond to relax. This happens thousands and thousands of times while the material is curing, which leads to this huge overall reduction in stress across the entire filling, all without actually weakening the final structure.
Now, this all sounds fantastic on paper, but for any materials scientist worth their salt, the big questions are always, does it really work, and what's the catch? So, let's look at the data.
This graph is really the smoking gun. What you're seeing here are two different materials. The open circles represent the material with our special stress-relaxing allyl sulfide group. The closed circles are a control material. It has a nearly identical group, propyl sulfide, that looks similar but can't do the AFCT reaction. The results are just stark. The control material builds up a ton of stress, and it just stays there. But the adaptable network with allyl sulfide, it develops way less stress to begin with, and you can even see it relax a bit over time. And what's really cool is that you can tune this effect. In graph A, you can see that the more of that allyl sulfide you add, the bigger the drop in stress. Makes sense. But graph B shows something else that's just as important, mobility. For those polymer chains to rearrange, they have to be able to move around a little. So, in materials with a lower glass transition temperature, a lower TG, the chains are more flexible and wiggly, and the stress relaxation works much, much better.
The numbers are just wild.
The original research showed that with the right formulation, this mechanism could get rid of as much as 75% of the final stress. I mean, that's not just a small tweak, that is a massive leap forward.
And here it is, the million-dollar question, because look, anyone can make a soft, weak material that doesn't build up stress. The real trick, the holy grail, is to make a low-stress material that is also tough enough to survive in your mouth for years.
And this is where the material design gets really elegant. By carefully choosing the other ingredients in the resin, the researchers could get that stress reduction without losing strength. This chart shows it all. It compares the strength and stiffness of a standard high-stress resin with their new, optimized low-stress version. And you can see there's no statistically significant difference. They actually did it. They got the best of both worlds, low stress and high strength.
So we've seen the lab results, we've seen the proof of concept, but what happens when this technology goes from the research bench and makes its way into the products that dentists are using on patients every single day? Okay, so in the real world, things get a little more nuanced. This amazing core idea has been put into practice in a few different ways. Some commercial products use what's called an addition fragmentation monomer, or AFM, which is based on that allyl sulfide chemistry we've been talking about. But others use a related, but different, class of molecules called RAFT agents. They also allow the network to rearrange, but their mechanism is a bit different. It involves shuttling a specific chemical group between chains.
And this table from a recent study is super revealing. It compares 3 different products. You've got TEC, a traditional control material, then TPF, which uses a RAFT agent, and finally FOB, which uses the allyl sulfide-based AFM. And the results are crystal clear. The Filtech 1 bulk, the one with the AFM, had the lowest shrinkage stress and the lowest amount of unreacted monomer leaching out, which is a great sign of a really well-cured material. Now, what's interesting is that the RAFT-based material had stress levels pretty similar to the control, even though it did help reduce that monomer leaching.
So what are the big takeaways from the real-world products? First, adding these kinds of adaptable links to the network makes for a better, more completely cured material, which is great for biocompatibility. Second, at least in this head-to-head comparison, the allyl sulfide-based AFM was way more effective at actually reducing stress than the RAFT agent was. And third, and this is so important for anyone designing materials, the magic ingredient isn't the only thing that matters. The whole recipe, from the initiator that kicks things off to all the other monomers in the soup, plays a massive role in how well the final product performs.
So let's just zoom out for a second and think about the big picture here. What does all of this really mean for the future of materials, not just in dentistry, but everywhere?
What we're looking at is more than just a better filling. It's a whole new way of thinking. For decades, the goal was to invent monomers that didn't shrink. That was the mission. Covalent adaptable networks completely flip the script. They say, you know what? The material can shrink. That's fine. We'll just build in a smart, dynamic way for it to manage its own stress. And that leads to a restoration that's just tougher, more reliable, and lasts way longer.
And that leaves us with this really exciting question for the future. Having bonds that can rearrange is amazing for relieving stress when the filling is being cured. But that filling has to sit in your mouth, a pretty harsh environment, for a decade or more. So the next great challenge is to perfect this dynamic chemistry. To design a material that's flexible and adaptable when you need it to be during those first few minutes of curing, and then becomes rock solid and stable for a lifetime. The person who solves that is going to truly revolutionize restorative materials.